Welcome to Module 3. This module is about the beast of bias. In this module, we will talk about the general assumptions of parametric tests based on the normal distribution. So this module covers chapter 6 from your textbook. So before going over the aims, I would like to define two terms here. We have parametric tests and non-parametric tests. So these are two main statistical procedures. So we can divide statistical procedures into two groups, parametric tests or non-parametric tests. Parametric tests rely on some assumptions, several assumptions. For example, one of the assumptions is about the shape of the distribution. But non-parametric tests, they rely on no or very few assumptions about the shape or parameters of the population, or whenever the assumptions of parametric tests are violated, we can use non-parametric tests. So let's go back to the aims. So in this module, we will talk about the assumption of normality. And when we say assumption of normality, we can kind of examine this assumption by using different methods like graphical displays, like using histograms or some kind of box plots. We can assess the skewness, kurtosis, and we can conduct some normality tests in order to kind of understand the assumption of normality. We can also, we have to actually, we have to also understand the homogeneity of variance by using Levin's test. And if any of these assumptions are violated, there are some different methods to kind of correct the data, like using some transformations, mathematical transformations, or doing some robust tests and some advanced statistical methods. So, as you all know, most of the time it is not feasible to do our measurements on all participants or all people in the population or in the community. It's not feasible. It is costly. It takes too much time. So for that reason, one of the solution is to draw some sample from the population of interest. Let's say if I wanna do some study on type 2 diabetes in the US, is it possible to do measurements on all people with diabetes in the US? So it's not possible. So for that reason, I would come and collect data from a subset of the population, of the individuals of interest, which is people with type 2 diabetes. So that will be my sample, right? And by getting sample, by collecting data from sample, I would like to estimate the parameters in the population. So when you see the term parameters, it's the values, the actual values in the population. But when I do collect data from sample of the individuals of interest, and I want to measure some like variables or outcomes, it is called statistics, not parameters anymore. So parameters are the values like means, standard deviations, proportions. It's called parameters in population. When we are talking about population, it's called parameters. But when I measure the values like mean, standard deviation, and all other types of quantities from sample, it's called statistics. So as I said, we have two types of statistical procedures. Statistical procedures can be parametric or non-parametric. For example, a linear regression, Pearson correlation, independent sample t-test, paired sample test, or paired sample t-test, ANOVA, um, correlation, Pearson correlation. These are all parametric tests. They all have some assumptions. And we have to understand those assumptions. We have to assess and evaluate those assumptions. Otherwise, if any of those assumptions are violated, either we cannot use those parametric tests, so we can use non-parametric tests, or we can do some kind of correction on our data. We can transform our data, our scores, raw scores, in order to use parametric tests. So here are the assumptions of parametric tests. So parametric tests based on the normal distribution, assuming linearity, additivity, normality, homogeneity of variance, and independence. And we are going to learn about each of these assumptions in next slides. So first thing, we have to make sure that our data has no outlier. We have to make sure that our raw data, our data set is free of outlier. Otherwise, our estimates, outliers will draw our estimates toward itself. So an outlier is an observation that appears to deviate markedly from other observations in the sample. So for example, let's say I measure BMI um, on 100 people. And the mean of that BMI, mean of the BMI in my sample is 25. I add one more participant to my data set. And the BMI of that participant is, let's say, 78 or 85. What happens to my mean? My means will be drawn toward that 85 or 78. So that 78 or 85 is my outlier. Why is it outlier? Because it is an observation that deviate greatly from other observations in my sample. So that is my outlier in my data set. BMI of 78 or 85 is an outlier. So there are a couple of different ways in order to identify outliers and also how to deal with outliers. I can go back and correct that if there is something, maybe there are some measurement error when I was measuring the BMI of that person, or let's say the BMI is 78 or 85. So that's my outlier. So I can drop that from my sample because that's an outlier. And it will give me a kind of inaccurate estimate when I'm doing some statistical analysis on my data set. So here is the effect of outlier. As you can see from this figure, we have two data sets. The orange one has no outlier and the blue one has an outlier. And as you can see, outlier kinds of it draws the graphs and the shape of our chart, our graph toward itself. So it's kind of giving us an inaccurate result. So, linearity and additivity. So when we say linearity, when we are measuring or assessing the relationship between two variables, we assume that the relationship is linear, which means the amount of change on one variable has to there has to be a linear relationship between a change on one variable compared to other variable when we are trying to assess the relationship between two variables. And we don't want to see a non-linear relationship. Otherwise, we cannot use some statistical tests. For example, for correlation or for regression, which we will talk about regression and correlation in next modules. Linearity is very important. It's one of the most important assumptions when we are using regression and correlation. So there are some relationships that are not linear. For example, the relationship between learning and time may not be linear. Learning a new subject shows rapid gains at first, then the pace slows down over time. So there is no linear relationship between these two variables. So if I want to kind of evaluate the association between learning and time and I graph it, I would not see a linear line between these two variables. So when this in this case, I would see a learning curve instead of just a linear curve. It will be a curve. It will be a kind of a curve graph. So that was about linearity. We have also additivity. So if I have several predictors, so the combined effect of several predictors is best described by adding their effects together. So if this assumption of linearity and additivity is not met, then our model is invalid. So we have to do some sorts of correction, or we have to use non-parametric tests instead of using parametric tests. So additivity is, let's say I have one outcome variable, but I have several predictors variable. So additivity means there should be a combined effect of those predictor variables on outcome variable. And I have to kind of model the interaction between those multiple predictor variables. So here we have three kind of graphs. We have two linear relationships and one curvy linear relationship. So the middle one and the left graph is linear. So it's just like a direct line between two variables. But on the right side, we can see a curve in the relationship between these two variables. So in that one, we cannot use some statistical tests because of the curvy linear relationship. The second assumption is a normal distribution. This is a very important point. When we talk about assumption of normality or normally distribution assumption, this means that the sampling distribution of the parameter estimate must be normally distributed. It doesn't mean that raw scores should be normally distributed. And if this normality assumption is violated, then we will have some errors in parameters, in confidence intervals, and the p-values are not valid. So we cannot just rely on the p-value if the normality distribution is violated. In small samples, uh, this is also a very important point. As long as our sample size is large, remember there is no exact number about how many people, how many observations I have to have in my data set. So there is no exact number, but if it is large, it's fairly large. Let's say I have 300 people in my sample or 100 people in my sample. In some cases, I have 1,000 people in my sample. So I would assume that the normality assumption is met. But again, it is better to kind of graph the data set in order to detect any deviation from normality. The third assumption, it's called homogeneity of variance. So we can test this. There are different kind of tests in SPSS in order to detect this assumption, in order to understand this assumption. The most important and the most common test is called the Levins test, and we will see it in next slides. So homogeneity of variance or homoscedasticity. This one talks about people in different groups. So when we have different groups, it means that the variance should be kind of similar to each other in different groups. So when we test several groups of participants, samples should come from populations with the same variance. For example, if I want to kind of compare um, adults to children, there should be a violation in homogeneity of variance because I have two different groups coming from two different populations, and the variance in these two populations are not going to be the same variance. So when we have any violation in homogeneity of variance, just like what we saw in normality distribution, we would have inaccurate estimate of parameters and the p value should be also invalid. So in order to kind of detect homoscedasticity or homogeneity of variance, as I said, there are different methods. We can graph it. We can graph our data set, our variables, in order to detect any kind of violation of homogeneity of variance. We can use Levens test. So I will show you how to do that, how to do Levens test. But remember, this is very important. If Levens test is significant, the variances are not equal, meaning homogeneity of variance is violated. So we want to see a non-significant Levens test. If our Levens test is not significant, we can conclude that the variances are equal and homogeneity of variance is met. And also we shouldn't use homogeneity of variance in large samples and in small samples. If homogeneity of variance is violated, we can use different methods. We can use some robust tests, we can adjust standard errors, we can also use other techniques and other methods. And other methods to kind of assess the homogeneity of variance is using variance ratio. So if we have two or more groups, we can divide the largest variance by smallest variance. If variance ratio is less than 2, homogeneity can be assumed. So here is two different types of data sets regarding homogeneity of variance. So on the left side, our data set is homogeneous. And as you can see, the variances is not spread out. But on the right side, our data set is heterogeneous and the variance is kind of spread out markedly. The last assumption is independence. Independence means that the data, the scores from one participant should be independent from the score of other participant or other observation. So this is an example on how to kind of spotting outlier. So we can graph it. If we graph our data set, we can easily detect outliers. So if you can see, there is a dot on the right side, which is far away from other dots on the graph. So that one is our kind of outlier. Or in the middle one, we have kind of a histogram here. But if you can see, there is a small bar on the right side of the middle graph. That one indicates an outlier. And on the bottom graph, we also have an outlier, which is far above other scores in the data set. So we can use scatter plot or histogram or box plot in order to detect outlier in our data set. How about spotting normality? How about testing normality? So again, to test normality, there are different methods. So we can use graphical displays like pp-plot or qq-plot, histogram, and also skewness and kurtosis values. We can also use some kind of other tests. We can use Kolmogorov-Smirnov test. And just like Levens test, if this test is significant, it means non-normal data. So just like Levens test, we want to see a non-significant p-value for Kolmogorov-Smirnov test. Again, just like Levens test, we shouldn't use this one in large samples and in very small samples. So we can use other methods to detect normality. So this is pp-plot and qq-plot. I'm gonna skip this because I want to show you how to work with SPSS on kind of assessing normality assumption. So we can use different methods in order to reduce bias. So let's say the assumptions are violated and we want to correct our data. There are different methods. Bootstrapping, it's one of the methods and it's advanced statistical method. So I'm not going to go into detail about that. But this method is based on medians and trims. We can trim our data. We can transform our data. Transformation is most common way of correcting data set. And among the transformation methods, the logarithm method is the most common one. So these are different methods of how to correct the bias, how to reduce the bias in the data set. And these are the transforming methods. So we have log transformation, which is the most common one. It reduces positive skewness. We have square root transformation. We have reciprocal transformation and other methods. There is one point regarding transforming dataset. Honestly, I have never used this method in my research. So most of the time, if there is a violation of assumptions, I prefer using non-parametric tests and not just transforming the data points. Sometimes when we transform data, when we kind of compute log of raw scores, it becomes hard to interpret the results. So that's why I do not use transformation. In order to kind of compute, um, kind of use mathematical transformation, in the SPSS, there is an option called compute variable. So we can we can utilize this option in order to transform our data. So for the class assignment, you will find the data set inside of the Blackboard folder. So there's a data set that you would need to use for your homework assignment. So I'm gonna open my SPSS. I'm gonna show you how to use um, different methods and how to assess the assumptions. Um, so I would like to go along with that, and you have to utilize other variables in order to assess the assumptions. So I'm gonna stop here and I'm gonna show you how to work on SPSS. So this is the data set you will find um, in your Blackboard folder. So this is SPSS file, but let's say if there is a file in Excel format or CSV format and you wanna use SPSS, so the easiest way to do is to go to File and then Import Data and then click Excel file and it will show you the pathway here. So you can just select the data file you have and then click open. So it will import Excel or other format mm, documents to SPSS. So I would like you to get familiar with this data set because probably we will use this for the rest of the semester. So this is our variable view. We have case ID, animation name, gender, favorite color, favorite animal, and we have some kind of continuous or numerical variables like caffeine intake. We have blood pressure, weight, height, BMI, and so on and so forth. So for this one, I'm gonna use let's see. I'm gonna use BMI, but you will need to use systolic blood pressure, SBP, or this diastolic blood pressure and um, caffeine intake. So first, I'm gonna go and get some descriptive statistics for BMI. So in order to do that, I need to go to Analyze, oops, Descriptive Statistics and Descriptives. And then I have to scroll down and find BMI, click on it, and click on this bottom here, or you can just click and drag it over here. It's totally up to you. So BMI is in my variable list. I'm gonna click on options. So mean, standard deviation, minimum, maximum, and let's say that's all for now. And then click OK. I hope you can see the descriptive statistics here. So the BMI, I have 80 observations for BMI. Um, the minimum is 16.7, the maximum is 28.8. So I would say that there is no outlier for BMI and the mean and standard deviation. This is what it gives me from descriptive statistics. And also I can go and get some frequency like histograms and the frequency tables. And let me do that here. So I'm gonna go back and then you need to go to analyze again, descriptive statistics and frequencies. Again, you have to scroll down and click on the BMI, click on this bottom here, and then make sure that this box is checked, display frequency tables. Let's double check this statistics option here. So here I can click on mean, median, mode, and then skewness, kurtosis, standard deviation, variance, range, and continue. And if you click on charts, you can choose any of these. Let's choose histogram. And if you check this box, it will show the normal curve on histogram. Let's click continue. We are not worried about the format option or style option. And then click OK. And there is an option here. It says create APA style tables, which is really interesting. And then click OK. Let's see what it gives me. So here it gives me skewness and the standard error of skewness, kurtosis, and standard error of kurtosis. So I need skewness and standard error of skewness in order to calculate the z-score and also for kurtosis as well. So here it gives me a histogram and the normal distribution kind of curve. I would, based on what I see, I would say it is some sort of normally distributed. So BMI is kind of normally distributed in my sample. So let's see. So if I have, as I said, I have skewness, kurtosis, and the standard error, I can measure the z-score. I'm gonna stop share here. I'm gonna share my PowerPoint slides so you can see what I'm talking about. So here, after clicking on statistics option, you can check this box here, skewness, kurtosis, and also dispersion options. And it gives you skewness and kurtosis here, as well as standard errors for skewness and kurtosis. So we can easily measure the z-score for skewness and kurtosis by dividing the skewness, subtract from 0, and then divide it by standard error for skewness. And it gives you the z-score. If it is greater than 1.96, then it is significant at p-value less than 0.05. If z-score is above 2.58 instead of 1.96, then p-value is significant at p less than 0.01. And if it is above 3.29, then the z-score is significant at p-value less than 0.001. So I would say here the z-score is not significant because it is not greater than 1.96. So z-score for kurtosis is not significant either because it's not greater than 1.96. So I would say my BMI is normal because the skewness and kurtosis is not significant. And for the Levens test, in order to do a Levens test, you have to go to Analyze, Descriptive Statistics, Explore, and then you will see a window like this, and then you have to kind of again drag and drop your variable to the dependent list, which is BMI here, and we have to have a factor list, gender, because if you remember the Levens test or homogeneity of variance, we assess the homogeneity of variance if we have a group of people, two or more groups. So gender is our grouping variable. And after choosing the factor list or grouping variable, we have to click on the plots and check histogram, factor levels together, check the normality plots with tests, and untransformed here. So let's do that and see what it gives me. So I'm gonna go to Analyze, Descriptive Statistics, Explore, and scroll down, choose BMI, dependent list, and gender is my factor list or grouping variable. And then click on statistics. So we are not worried about this option. Click on plots, check histogram. I'm just gonna uncheck stem and leaf, and normality plots with tests and untransformed, and then continue. Let's check options. There's nothing to do here, and then bootstrapping, there's nothing here to do. So display both statistics and plots and click OK. So it gives me PP plots, QQ plots in order to detect any kind of a violation of assumptions here, especially for homogeneity of variance. Let me find the statistics here. So I have tests of normality here. So if you can see, the Smirnov test is not significant. So I would assume that the normality assumption is met. And for the Levens test, I would like to see this one based on median. So the Levens test is not significant either. So I would assume I can conclude that the homogeneity of variance assumption is met for BMI. So after doing this for your variables, um, I would like you to watch the another video about how to kind of write up example, how to write up the results in a Word document using APA style, and then report your results there. So let me go back to PowerPoint slides, and I'm gonna show you here again one more time. So for the homogeneity of variance assumption, again, you need to go to Analyze, Descriptive Statistics, and Explore. And after that, you have to choose your variable So for example, you are going to use caffeine. So just drag and drop the caffeine variable into this dependent list box, and then factor list, it can be gender again. And then click on plots, make sure this is on transformed, check this box over here, normality plots with tests and histogram, and then click continue and then click OK. And it gives you kind of these tables and a bunch of graphs about PP plot and then QQ plot. So for the test of normality, we will see Kolmogorov-Smirnov test here, which is not significant, so our normality assumption is met. And for the homogeneity of variance, we have Levin's test. Again, I would like to look at this based on median row over here. So the Levin's test is 0.598 and the significance level is 0.4042, which is not significant because it is less than 0.05. So I would conclude that the homogeneity of variance or homoscedasticity assumption is met.